Yo, what's up, guys? Today we're gonna be doing some computer science. It's just gonna be some of my classwork and stuff like that. So hopefully you enjoy.
In this module of Core Python Functions and Functional Programming, we'll look at Python's extended argument syntax for accepting arbitrary numbers of positional arguments and arbitrary keywords. We'll also look at how to specify positional-only and keyword-only arguments. As a complement to extended argument syntax, we'll also look at Python's extended call syntax. And we'll discover Python's idiom for forwarding arbitrary function arguments. We've already been using functions which support extended argument syntax, although you may not have realized it. For example, have you wondered how it is possible for print to accept 0, 1, 2, or in fact any number of arguments? Another example we've seen is the use of the str.format method, which can accept arbitrary named arguments corresponding to the format placeholders in the string. In this section, we'll learn how to define functions, or more generally, callables, which can accept arbitrary positional or keyword arguments. Let's start with positional arguments. Drawing an example from geometry, let's write a function which can return the area of a two-dimensional rectangle, the volume of a three-dimensional cuboid, or indeed the hypervolume of an n-dimensional hypercuboid. Such a function needs to accept an arbitrary number of numeric arguments and multiply them together. To do this, we use a special argument syntax where the argument name is prefixed by a single asterisk. Before we implement the computation, we'll simply print out the value of args and its type using the built-in type function. Notice that the asterisk does not form a part of the argument name, and the argument name we have chosen here, args, is widely used in this case by convention, although it is by no means necessary. Colloquially, this form is called star args. Now, let's call our function a few times. We can see that args is passed as a tuple which contains the function arguments. Knowing this, it's a simple matter to write code to multiply all the values in the tuple together to get the result. Redefining hypervolume and using a more documentary name for the argument gives us this. The function works by obtaining an iterator I over the tuple and using next to retrieve the first value, which is used to initialize a variable v, in which the final volume will be accumulated. We then use a for loop to continue iteration with the same iterator to deal with the remainder of the values. We can use the function to compute the areas of rectangles, the volumes of cuboids, and hypervolumes of hypercuboids. It also generalizes nicely down to lower dimensions to give us the length of lines. However, if called with no arguments, the function raises stop iteration, exposing an implementation detail about which clients of our function should be unaware. There are a couple of approaches to fixing this. One change could be to wrap the call to next in a try-except construct and translate the exception into something more meaningful for the caller, such as the type error that is usually raised when an insufficient number of arguments is passed to a function. We'll take a different approach of using a regular positional argument for the first length and the star args to soak up any further length arguments. Using this design, the function continues to work as expected when arguments are supplied, and raises a type error exception when insufficient arguments are given. At the same time, the revised implementation is even simpler and easier to understand than the previous version, which used an iterator. Later in this course, we'll show you how to use the functools.reduce function, which could also have been used to implement our hypervolume function. When you need to accept a variable number of arguments with a positive lower bound, you should consider this practice of using regular positional arguments for the required parameters and star args to deal with any extra arguments. Note that star args must come after any normal positional arguments, and that there can only be one occurrence of star args within the argument list. The star arg syntax only collects positional arguments, and a complementary syntax is provided for handling keyword arguments. Let's look at that now. Arbitrary keyword arguments can be accepted by callables that use an argument prefixed by a double asterisk. Conventionally, this argument is called quargs, or kwargs, although depending on your situation, you may care to choose a more meaningful name. Let's make a function which returns a single HTML tag as a string. The first argument to the function will be a regular positional argument which will accept the tag name. This will be followed by the arbitrary keyword args construct, to which tag attributes can be passed. As before, we'll perform a simple experiment to determine how the keyword arguments are delivered. When we call the function with some suitable attributes to create an HTML image tag, like this, we can can see that the arguments are transferred to our keyword arguments formal parameter as a regular Python dictionary, where each key is a string bearing the actual argument name. Now, we'll go ahead and implement our tag function properly, using a more descriptive name than quarks. Here, we iterate over the items in the attributes dictionary, building up the result string as we go. It's worth pointing out at this stage that the strud.format method we call here also uses the arbitrary keyword args technique to allow us to pass arbitrary named arguments corresponding to our replacement fields in the format string. This example also shows that it's quite possible to combine positional arguments and keyword arguments. In fact, the overall syntax is very powerful, so long as we respect the order of the arguments we define. First, star args, if present, must always precede star quarks, so this isn't allowed. Second, any arguments preceding star args are taken to be regular positional arguments, as we saw in the hypervolume example earlier. Thirdly, any regular arguments after star args must be passed as mandatory keyword arguments. Failure to pass them as keyword arguments results in a type error. There are situations where you will want to use mandatory keyword arguments without accepting an arbitrary number of positional arguments. To support this, Python allows you to omit the name of the star args argument. The arguments following the asterisk can only be passed to the function as keyword arguments, but Python will not allow you to pass extra positional arguments to the function. Fourthly, and finally, we have the star quarks arbitrary keyword arguments, which, if present, must be last in the argument list. Any attempt to define an additional formal argument after star quarks results in a syntax error. You should take particular care when combining these language features with default arguments, which have their own ordering rule, specifying that mandatory arguments must be specified before optional arguments at the call site. PEP 570 introduced support for positional-only arguments, and these are available in Python 3.8 and later. Whereas keyword-only arguments can only be passed as keyword arguments, positional-only arguments can never be passed with a keyword. To specify positional-only arguments, you include a / in your function's argument list. All arguments before the / are positional only, so you can pass them to the function positionally. Any attempt to pass them by keyword will result in a type error. You may wonder why Python includes this feature, and it turns out that there are some good reasons. One reason is to provide parity in pure Python code with modules implemented in C and other languages. These extension modules can, and historically have, implemented functions with positional-only arguments using techniques that aren't available in pure Python. An example of a function like this is range. More importantly, though, this feature allows you to prevent certain argument names from becoming part of your function's APIs. By prohibiting users from using keywords for some arguments, you prevent them from creating dependencies on those names. This can be particularly useful when the argument names have no useful semantic meaning and are only defined at all because Python requires it, as with our number length example from before. Before moving on, we should point out that all the features of the extended argument syntax apply equally to regular functions, lambdas, and other callables, although it's fair to say that they are rarely seen in combination with lambda in the wild. The complement to extended formal argument syntax is extended call syntax, which allows us to use iterable series, such as a tuple, to populate positional arguments, and any mapping type, such as a dictionary, that has string keys, to populate keyword arguments. Let's go back to a simple version of print args, which only deals with mandatory positional and star args arguments. We'll now create an iterable series, in this case a tuple, although it could be any other conforming type, and apply it at the call site for print args using the asterisk prefix to instruct Python to unpack the series into the positional arguments. Notice that the use of the star syntax in the actual arguments does not necessarily need to correspond to the use of star in the formal argument list. In this example, the first two elements of our tuple have been unpacked into the mandatory positional arguments, and the last two have been transferred into the args tuple. Similarly, we can use the double asterisk prefix at the call site to unpack a mapping type, such as a dictionary, into the keyword arguments, mandatory or optional. First, we'll define a function color, which accepts 3 arguments, red, green, and blue. Each of these 3 arguments could be used as either positional or keyword arguments at the call site. At the end of the argument list, we add star quarks to soak up any additional keyword arguments that are passed. Now we'll create a dictionary to serve as our mapping type of keyword arguments and apply it at the function call site using the double star prefix. Notice again how there's no necessary correspondence between the use of star star in the actual arguments versus the use of star star in the formal argument list. Items in the dictionary are matched up with the arguments, and any remaining entries are bundled into the quarks parameter. Before moving on, we'll remind you that the dict constructor uses the star star quarks technique to permit the creation of dictionaries directly from keyword arguments. We could have used that technique to construct a dictionary K in the previous example, but we didn't want to make the example more complex than necessary. Otherwise, we could have constructed K as K equals dict, red equals 21, green equals 68, blue equals 120, alpha equals 52. One of the most common uses of star args and star star quarks is to use them in combination to forward all arguments of a function to another function. For example, suppose we define a function for tracing the argument and return values of other functions. We pass the function whose execution is to be traced, but that function could take any arguments whatsoever. We can use extended argument syntax to accept any arguments to our tracing function, and extended call syntax to pass those arguments to the traced function. We'll trace a call to int to demonstrate that trace can work with any function without advanced knowledge of the signature of that function. Let's review what we've covered in this module. We saw how Python's extended argument syntax allows us to accept arbitrary numbers of positional arguments, as well as arbitrary keyword arguments in our functions. We also saw how to specify keyword-only and positional-only arguments to functions and other callables. We looked at Python's extended call syntax for applying the elements and iterables and mappings to function parameters. And we saw how to combine these features for perfect argument forwarding. In the next module of Core Python Functions and Functional Programming, we'll investigate local functions and the key to how they operate, closures. Thanks for watching, and we'll see you in the next module.
All right, guys. Thank you for watching, and hopefully you learned with me a little bit.